Hello everybody, I am Anu Joseph. By now you are familiar with the absorption, metabolism, storage and transport of vitamin A. In this session, we shall come to the most important aspect of the study of vitamin A, namely its functions, deficiency, recommended dietary allowance, diagnosis and assessment of availability of vitamin A. How much of vitamin A is actually required by the human body at different physiological stages? Let us take a look. The recommended level of intake of vitamin A is set to prevent clinical signs of deficiency, allow for normal growth and other vitamin A dependent functions, and to maintain an acceptable total body reserve of the vitamin. This reserve helps offset periods of low intake or increased need resulting from infections and other stresses. The intake should be adequate to reduce the risk of vitamin A related severe morbidity and mortality on a population basis. It should also account for proportionate bioavailability of preformed vitamin, which is about 90%, and provitamin A carotenoids from a diet that contains sufficient fat, which is at least 5 to 10 grams. Bioavailability of carotenoids varies widely by source. ICMR recommended dietary allowance for retinol and beta-carotene 2010 are as follows. Normal adult men and women require 600 micrograms of vitamin A and 4,800 micrograms of carotene, whereas in pregnancy it is increased to 800 microgram and 6,400 micrograms. In lactation, the requirement is further increased to 950 micrograms and 7,600 micrograms. Infants require 350 micrograms of vitamin A and 2,100 micrograms carotene, and increasing during the lifespan until the requirement in adolescence is same as that for adults. A conversion ratio of 1:8 is used in the conversion of beta carotene to retinol. ICMR recommends that at least half the intake should be drawn from animal sources to ensure adequacy, at least in vulnerable groups like pregnant and lactating women. What are the factors taken into consideration when computing the vitamin A requirements for the different age groups? Vitamin A requirements for infants are calculated from the vitamin A provided in human milk. During at least the first 6 months of life, exclusive breastfeeding can provide sufficient vitamin A to maintain health, permit normal growth, and maintain sufficient stores in the liver. During pregnancy, additional vitamin A is needed for the growth and maintenance of the fetus, for providing a reserve in the fetal liver, and for maternal tissue growth. In lactation, if the amounts of vitamin A recommended for infants are supplied by human milk, mothers should absorb as much in their diets to replace maternal losses. After the infant reaches the age of 6 months or when solid foods are introduced, the mother's need for additional amounts of vitamin A lessens. There is no indication that the vitamin A requirements of healthy elderly individuals differ from those of other adults. However, diseases that impede vitamin A absorption, storage and transport might be more common in the elderly than in the other age groups. Let us now look into the role of vitamin A. We have seen earlier that there are 3 active forms of vitamin A, commonly referred to as the retinoids, namely retinal, retinol and retinoic acid. These 3 active forms of vitamin A each serve different functions. Retinal is required for rhodopsin formation and vision. Retinol plays a role in reproduction, while retinoic acid is the principal hormonal metabolite required for proper growth and differentiation of epithelial cells. We shall now discuss in detail the functions of vitamin A. The most important function of vitamin A is in normal vision. Vitamin A is required for the formation of the photoreceptor rhodopsin, which is a complex of retinal and the vision protein opsin. The light-sensitive pigment rhodopsin occurs embedded in the membrane of the rod cells in the retina at the back of the eye. When light passes through the lens, it is sensed in the retina by both rod cells and cone cells. Rod cells are responsible for black and white vision and cone cells for color vision. In rod cells, the exposure of rhodopsin to light causes 11-cis-retinol to be released from opsin, resulting in a conformational change in the photoreceptor that activates the G protein transducin. Transducin activation leads to the closure of the sodium channel in the membrane and the hyperpolarization of the rod cell, which propagates a nerve impulse to the brain that is perceived as light. This is also referred to as the Wall's visual cycle. The speed at which rhodopsin is generated relates to the availability of retinol. Night blindness is usually an indicator of inadequate available retinol, but it can also be due to the deficit of other nutrients which are critical to the regeneration of rhodopsin, such as protein and zinc, and to some inherited diseases such as retinitis pigmentosa. The second most recognized function of vitamin A is its role in cell differentiation. Retinoic acid acts as a hormone to affect gene expression and thus control cell development. Retinoic acid and retinol help maintain healthy epithelial tissue, the protective tissue covering body surfaces, especially the skin and the inner mucous membranes in the nose, throat, eyes, GI tract and genitourinary tract. These tissues are the primary barrier to infection. It makes the linings of the outside of the body and inside cavity smooth. In the presence of adequate amounts of vitamin A, they form mucus secreting goblet cells, but in the deficiency of vitamin A, they are keratinized. Vitamin A plays a role in maintaining the integrity of the cell membrane. It is also essential for healthy skin. Vitamin A is also important as an antioxidant and the production of immune cells responsible for fighting bacterial, parasitic and viral attacks. Vitamin A is also known to be involved in the synthesis of certain glycoproteins that are key components of the plasma membrane. Glycoproteins are important for cell communication, recognition, aggregation and adhesion. Retinol functions in the synthesis of certain mucopolysaccharides necessary for mucus production and normal growth regulation. This is accomplished by phosphorylation of retinol to retinyl phosphate. Retinol and retinoic acids are involved in the earliest process of embryogenesis, including the differentiation of the 3 germ layers, organogenesis and limb development. In children, there is evidence to indicate that vitamin A supplements are beneficial for reducing morbidity and mortality among HIV infected children. Vitamin A intake has a complex relationship with cancer prevention. While small doses of vitamin A or beta carotene appear to help prevent cancer, higher doses seem to have the reverse effect. The anti-cancer effects of beta carotene appear to stem from its antioxidative ability to scavenge for reactive oxygen species, as well as through its conversion to vitamin A, which can improve immune function, in addition acting to block certain carcinogenic processes and inhibit tumor cell growth. However, an excessive intake of beta carotene appears to have carcinogenic effect, hence dosage seems to be an important factor in beta carotene action. Vitamin A as retinol is essential for reproductive processes in both males and females, although the mechanism of its actions are unclear at present. It is necessary for spermatogenesis in the males and normal estrous cycle in the females. In the absence of vitamin A during fetal development, various malformations occur. It also causes sterility and testicular degeneration in males and abortions in females. Part of this is due to the role of vitamin A in maintaining epithelial tissue. The importance of vitamin A status during pregnancy on maternal and child health has been recognized only in the recent years. Serum retinol less than 20 microgram per dl was found to be associated with preterm deliveries according to the studies conducted at NIN in the year 2000 to 2001. The antioxidant function of vitamin A is relegated specifically to the carotenoids and not the preformed vitamin A. Carotenoids function as antioxidants because of the ability to scavenge free radical substances, thus protecting the person from oxidative stress. It helps maintain stability of the cellular biological membrane. In deficiency of vitamin A, cilia are lost and thus the body is vulnerable to infections, as cilia prevents accumulation of foreign material on epithelial cells of the GI tract, respiratory tract and others. Vitamin A also play an important role in bone development and growth. Vitamin A is essential for the normal development of skeletal, teeth and soft tissues. Vitamin A plays an important role in bone maintenance through involvement with osteoblasts and osteoclasts. Vitamin A is also involved in the production of red blood cells, which are derived from stem cells that are dependent upon retinoids for their proper differentiation. In addition, vitamin A appears to facilitate the mobilization of iron stores to developing red blood cells, where it is incorporated into the oxygen carrier hemoglobin. Now that we have seen the functions of vitamin A, let us now see the consequences of its deficiency on the body. Deficiency symptoms show up after liver reserves of the vitamin have been depleted. These symptoms can also be the result of a deficiency of protein or zinc, either of which reduces the amount of vitamin A released from liver stores. Symptoms may result from low dietary intakes, interference with absorption and storage, or interference with the conversion of keratin to vitamin A. Before we go into the clinical signs and symptoms of vitamin A deficiency, let us briefly delve into the causes of deficiency. Primary vitamin A deficiency is usually caused by 1. Prolonged dietary deprivation due to inadequate dietary intake. This is endemic in areas such as southern and eastern Asia, where rice, devoid of beta carotene, is a staple food. Animal foods provide preformed vitamin A. Since these are expensive, the poor communities depend on plant foods which provide only provitamin A. 2. Inadequate intestinal absorption. The common childhood infections like measles, diarrhea, respiratory tract infection and infestations like ascariasis and giardiasis interfere with the absorption of vitamin A. 3. Increased excretion. Vitamin A excretion is increased in cancer, urinary tract disease and chronic infectious disease. 4. Ignorance. Due to female illiteracy and the consequent ignorance, supplementation with vitamin A rich foods is delayed and certain rich sources of beta carotene like green leafy vegetables and papaya are avoided with the belief that these are deleterious to the health of children. Due to lack of awareness, the community does not make use of primary health services like diarrhea control, immunization, vitamin A supplementation and other basic health services. 5. Improper methods of cooking. Boiling or prolonged heating at high temperature has deleterious effects in the retention of keratins. Cooking in the presence of oil helps in retaining beta carotene better. Vitamin A is lost by oxidation. Secondary vitamin A deficiency may be due to decreased bioavailability of provitamin A carotenoids, and interference with absorption, storage or transport of vitamin A. Interference with absorption or storage is likely in celiac disease, cystic fibrosis, pancreatic insufficiency, duodenal bypass, chronic diarrhea, bile duct obstruction, giardiasis and cirrhosis. Vitamin A deficiency is common in prolonged protein energy undernutrition, not only because the diet is deficient, but also because vitamin A storage and transport is defective. Coming to the symptoms and signs of vitamin A deficiency. One of the earliest manifestation of vitamin A deficiency is night blindness, also known as nyctalopia, and more severe deficiencies include ocular changes leading to blindness, particularly in young children. Though there has been a significant reduction in severe clinical forms of vitamin A deficiency over the last 3 decades, vitamin A deficiency is still a public health problem, with 40 to 60% of the child population in developing countries showing inadequate biochemical status of vitamin A. Very low intakes, poor bioavailability of provitamin A from the predominantly vegetarian diet, and recurrent infections are thought to be the main reasons for widespread prevalence of vitamin A deficiency. Night blindness is difficulty for the eyes to adjust to dim light. Affected individuals are unable to distinguish images in low levels of illumination. People with night blindness have poor vision in the darkness, but see normally when adequate light is present. Vitamin A deficiency affects vision by inhibiting the production of rhodopsin. Vitamin A deficiency in cells can lead to keratinization of cells, leading to xerosis or drying. Bitot spots appear as foamy, whitish accumulations appearing in the conjunctiva of the eye. Other ocular manifestations such as night blindness and xerophthalmia. In the xerophthalmia, the conjunctiva becomes dry and the eye is no longer able to form tears. The conjunctiva becomes thickened and wrinkled, and the cornea can become ulcerated, which can lead to total blindness, the condition known as Keratomalacia. Goblet cells are responsible for the secretion of mucus, and their absence results in xerophthalmia, where the eyes fail to produce tears. Dead epithelial and microbial cells accumulate on the conjunctiva that can lead to infection and probably blindness. In advanced deficiency, the cornea becomes opaque due to ulceration, which can lead to irreversible blindness known as keratomalacia. Natural killer cell activity and phagocytosis are also impaired with vitamin A deficiency. Immunity is generally impaired. Women of reproductive age are also thought to be vulnerable to vitamin A deficiency during pregnancy and lactation because they often report night blindness and because their breast milk is frequently low in vitamin A. The prevalence of night blindness due to vitamin A deficiency is also high among pregnant women in many developing countries. It also contributes to maternal mortality and other poor outcomes in pregnancy and lactation. Keratinization of the skin and of the mucous membranes in the respiratory, GI and urinary tracts can occur. Drying, scaling and follicular thickening of the skin and respiratory infections can result. The younger the patient, the more severe are the effects of vitamin A deficiency. Growth retardation and infections are common among children. Mortality rate can exceed 50% in children with severe vitamin A deficiency. Vitamin A deficiency can occur in individuals of any age. However, it is a disabling and potentially fatal public health problem for children under 6 years of age. Vitamin A deficiency related blindness is most prevalent in children under 3 years of age. This period is characterized by high requirements of vitamin A to support early rapid growth, the transition from breastfeeding to dependence on other dietary sources of the vitamin, and increased frequency of respiratory and gastrointestinal infections. The increased mortality risk from concurrent infections extends at least to 6 years of age and is associated with both clinical and subclinical vitamin A deficiency. Vitamin A deficiency is a leading cause of preventable childhood blindness. Approximately 250,000 to 5 lakh malnourished children in the developing world go blind each year from a deficiency of vitamin A, approximately half of whom die within a year of becoming blind. Vitamin A deficiency also diminishes the ability to fight infections. In countries where children are not immunized, infectious disease like measles have higher fatality rates. Let us move on to the identification and diagnosis of vitamin A deficiency. Ocular signs of vitamin A deficiency are measured by clinical examination and history and are quite specific in preschool age children. However, these are rare occurrences that require examination of large populations to obtain incidence and prevalence data. The most frequently occurring clinical indicator is night blindness, which is the earliest manifestation of xerophthalmia. In mild form, it is generally noticeable after stress from a bright light that bleaches the rhodopsin, which is also known as visual purple, found in the retina. Vitamin A deficiency prolongs the time to regenerate rhodopsin, thus delays adaptation time in a dark environment. No field applicable objective tool is currently available for measuring night blindness in children under 3 years of age and hence is not recommended at the community level. If dark adaptation is impaired, serum levels of retinol are measured. Normal range is 28 to 86 microgram per dl. However, levels decrease only after the deficiency is advanced because the liver contains large stores of vitamin A. Also, decreased levels may result from acute infection which causes retinol binding protein and transthyretin levels to decrease transiently. Indicators of vitamin A status. There is no single effective indicator in determining vitamin A deficiency in the community. In the case of children and pregnant women, a record of dietary intake and history of night blindness are found to be the most effective. Vitamin A status may be assessed in a variety of ways, including clinical assessment for Bitot spots, measurement of dark adaptation threshold, and electrophysiological measurements including electroretinograms to measure the level of rhodopsin and its rate of regeneration. The following are the methods. 1. Dark adaptation test. This test measures the speed of recovery of vision in dim light. It is an accurate and sensitive measure of vitamin A status. 2. Liver vitamin A concentration. Liver vitamin A concentration in excess of 20 microgram per gram of wet liver is considered to indicate a sufficiency of vitamin A in the body. Concentrations lower than 5 microgram per gram indicates a high risk of vitamin A deficiency. 3. Serum vitamin A. It is a less sensitive test than the liver vitamin A concentration. Serum vitamin A concentration below 10 microgram per dl indicates a state of vitamin A deficiency. 4. The relative dose response test. Administration of small doses of vitamin A in a depleted state results in a prompt release of retinol binding protein, and this increases circulating vitamin A, which is the principle behind the relative dose response test. In this test, a small amount of vitamin A is administered orally or intravenously in the form of retinyl esters, about 450 to 1000 milliliters in oils after a period of fasting and the change in the serum vitamin A concentration that occurs in response to this dose is measured over several hours, namely 5, before serum vitamin A returns to initial low levels. In persons with poor vitamin A status, the increase in serum vitamin A concentration is significantly greater and a longer time elapses before the concentration returns to the initial low levels. RDR is measured using the formula 5-hour plasma retinol minus initial retinol plasma by the 5-hour plasma retinol concentration into 100. Recently, the ratio of circulating retinol binding protein by the transthyretin is suggested as an improved index of vitamin A status. Fifth test, conjunctival impression cytology. This is a simple and rapid method. It measures the reduction in goblet cells and the derangement of epithelia on the conjunctiva of the eye, which occurs with impaired vitamin A status. A piece of filter paper is brought briefly into contact with the conjunctiva of the eye and then removed. The cells which adhere to the paper are examined under the microscope after suitable fixing and staining. The cell changes characteristic of xerosis can be identified before the clinical symptoms of vitamin A deficiency becomes evident during eye examination. The method is difficult to carry out in children younger than 3 years of age who are at high risk of vitamin A deficiency to obtain a suitable sample of cells. The sixth test is the metabolic indicator. Circulating levels of retinyl B-glucuronide has been proposed as a metabolic indicator of vitamin A status. The seventh is the functional tests. 2 biochemical functional tests based on increased erythrocyte oxidative stress and ammonia nitrogen excretion have been developed at NIN. Ammonia nitrogen by the creatinine level was found to be useful in children and pregnant women to indicate the functional inadequacy of vitamin A status. The eighth test consists of examining the breast milk retinol. In case of lactating women, dietary history and breast milk retinol are found to be the most effective combination of indicators as indicated by the WHO. The ratio of vitamin A to fat in breast milk is a better indicator of maternal vitamin A status than vitamin A concentration alone, which can vary greatly during the day. The ninth test is a tear fluid retinol assessment. Tear fluid vitamin A concentration can also be considered as an indicator. The table depicts the biochemical indices of vitamin A status, which shows the various normal values for the different tests. Thus, to sum up, we have seen the recommended dietary allowances of vitamin A for the different age groups, the important role played by vitamin A in the human body, the deficiency signs and symptoms, and the methods of assessing and diagnosing the status of vitamin A in the body. We now come to the end of this module. Goodbye.